All right, so it's time to talk about the definite integral. In a previous video, we talked about indefinite integrals, and indefinite integrals are basically just find an antiderivative for the function. This is a definite integral, which means basically find the exact area between the curve and the x-axis. Okay, and the notation for it is similar. We have this big tall S sort of thing here. Okay. And you put the function inside here. Okay, so we have the integral sign. We have the integrand, just like we did before. And we have the differential, which tells us which variable we're integrating with respect to. But the difference is a definite integral is like for a specific function on a specific interval, a to b. So we need to denote the interval here with the values a and b. And you put those below and above, like sort of at the bottom and at the top of the integral sign. So when you see it with numbers there, then that means that we're talking about a definite integral instead of an indefinite integral. Okay, and what this is it's defined as the limit as n goes to infinity of a Riemann sum with n rectangles. And if you're using right-hand endpoints in particular, you can do a plus I delta x inside your f there. So this should be f of the sample point on the ith subinterval, but for right-hand endpoints, you can use the formula a plus I delta x, and I recommend doing that just because it's sort of the simplest way to calculate it. And you're going to get the same answer no matter what you use, so it doesn't really matter whether you use left-hand endpoints or right-hand endpoints or random points or whatever. It's going to be the same, so might as well just use the simplest one. So there we go. So that's a definite integral, and we're going to do an example of this now using what function? I forgot. We're going to use the function. Shoot, where'd it go? For this example, we use the function f of x equals x squared, and the interval 0 to 8. So let's say that's y equals x squared. Here's 8. We're talking about calculating the exact area underneath that curve on the interval from 0 to 8. So what is that area exactly? There's no geometric formula that can do that, right? Because one of the boundaries of that area is a parabola. No geometric formula tells us area bounded by a parabola. Okay, we can do circles, we can do triangles, we can do anything anything whose boundary is made up of straight lines, but we cannot do parabolas until now. All right, so the way we're going to do this to calculate it exactly is we're going to set up a Riemann. We're going to set up a Riemann sum, and then we're going to do a limit of that. So we're going to be talking about the integral from 0 to 8 of x squared dx. That's the definite integral that we're talking about doing here. Okay, it's 0 to 8. This is x squared, and we're integrating with respect to x, which just means x is the independent variable here. Okay, so a couple of things. The number of rectangles. Let me put a couple of things over here. Number of rectangles is n. Okay, we're not going to specify the number of rectangles because we want to take a limit as that n approaches infinity, right? So that increase the number of rectangles to infinity. Then delta x, the width of each rectangle, is going to be 8 minus 0, 8 units, because that's the length of the whole interval, divided by n, right? So 8 over n, in other words. And then ci, the ith sample point from each subinterval, can be written as a, which is 0, plus I times delta x. So delta x, we already figured out, was 8 over n. So it's 0 plus I times 8 over n, or in other words, it's going to be like 8I over n, basically. Okay, so it's I times delta x and then plus 0. So in this case, we have that. That's the formula for our ith our ith sample point. So now, let's do this. Okay, so we've got our limit, and we're going to do a sum, I equals 1 to n, and we're going to take the function, for now I'm just going to call it f, of a plus I delta x, which is going to be 8I over n, and then that times delta x, and delta x is 8 over n. So there we are. So far that's specifying the sample points on the inside of the function there, and it's specifying the width of the rectangles delta x. But this is not specifying the function. We could specify the function, of course. The function is x squared. So let's, in our next step, let's go ahead and do that. I'm going to have sum I equals 1 to n. So now we have to apply the function x squared with the inputs 8i over n. So what I'm going to do for that is put the 8i over n in parentheses and then square it. So there's the function, the squaring function being applied here. I still have to multiply by 8 over n. Okay, there we go. So now it's time to start simplifying. Okay, we've put all the pieces in all the right places. So now, first thing I'm going to do is multiply this out. We're going to get 8 squared, 64, times another 8. All right, so that's going to be 512. We're going to have 512. Then we're going to have I squared, right? There's no more i's over here, so it's just I squared. In the denominator, we'll have n squared, but then we'll multiply by another n. So overall, we're going to have n cubed in our denominator. So there's what we have there. So now, let's think about the fact that this sum is over I, right? The sum, the index for the sum is I. So as far as the sum is concerned, the only variable is I. That means the 512 divided by n cubed, that entire thing can be viewed as a constant. So let's factor that out. We have 512 over n cubed times the sum I equals 1 to n of I squared, like that. So there we go. Now, the other thing we can do is say, well, as far as this limit is concerned, n is the variable, right? The limit is with respect to n. So anything that's constant inside that limit could come out, right? So this n cubed in the denominator depends on n, and the value of this sum is going to depend on n because n is the number of terms we're adding together. So that's going to change if n changes. 512 is constant, so we might as well pull that out of the limit. So you see, I'm going to pull that out here. Now, left over inside here, instead of 512 over n cubed, is just 1 over n cubed. And now, now that we've basically pulled out the constants here, that is a very simple sum formula that we can use. This, the sum of n squared, you can look it up. Where'd my paper go? I'll give you these formulas, and I'm not going to make you memorize. I'm not going to make you memorize these formulas. Here's the one we want right here. That's summing up I squared. So it looks like it's n times n plus 1. All right, so, okay, it's right here. This is where I'm putting it. I'm going to put n times n plus 1 times 2n plus 1 all over 6. There we go. Got it. So, there we go. So now I think we're almost done, because now we have we had a sum, but we've put that sum, we've kind of simplified it down so that we could take that sum and replace it with a closed form. And now we can do a limit of this as n approaches infinity. You might think that we need to multiply this out. We actually don't necessarily need to multiply this out entirely. If we think a little bit critically, we can determine that this is going to be a cubic polynomial in the numerator, because we have n times n plus 1 times 2n plus 1. There's going to be 3 n's multiplied together, so we'll get n cubed. There's 1 out here, so that doesn't matter. And the leading coefficient of that polynomial is going to be 2. So we're going to have 2n cubed. Let me write it out. You don't need to necessarily write this step, but it's basically going to be 2n cubed plus a bunch of other stuff. And the other stuff is not really going to matter, because the denominator is also a cubic polynomial. It's n cubed times 6. 6n cubed. And you may have noticed that what you get when you take the limit of a rational function whose numerator and denominator are the same degree is just the ratio of the leading coefficients. In fact, in pre-calculus or college algebra, you get taught that as a rule, right? And the justification for it is what I taught you when we learned about limits at infinity. But but we can use that rule here. So this is going to be, the limit of this is just going to be 2 over 6, or 1/3. So we're going to have 512, which we factored out, times 2 over 6. So 512 times 1/3, or 512 over 3, which is 170.6 repeated. And that, my friends, that is the exact area underneath the parabola x squared between 0, x equals 0, and x equals 8. That is 170 and 2/3 square units. All right?